Thank you. So none of this will be more complicated than the mirroring macOS setup process we just went through. So my name's Jan. I work at Brave, and today I'm here to talk to you about building more secure cryptocurrency wallets. So how many people have heard of Brave already? Hopefully, okay. Okay, most of you. That's better than zero. For those of you who don't know, we're an open source and privacy-focused web browser. We launched in 2016, and I've been the security chief at Brave since 2015. And these days, we also have a search engine and a VPN. So you might ask, why would someone use Brave over Chrome or Firefox? Well, we're one of the few browsers that has a default of privacy of blocking ads and trackers. We're fully open source based on Chrome. We also have support for Tor and VPN for better network privacy. And one of the coolest things we do is block fingerprinting, which is a way that websites can track users without cookies. So if there's no cookies, then websites might try to infer details about a user's graphics card or CPU or audio driver in order to build a fingerprint for them that they can use to track them across the web. So as far as I know, we're one of the only browsers that tries to do that kind of detection of fingerprinting and block it. And that, at this point, most people ask, so how can we support the web without ads? Because that is how most websites make money. And our answer to this is BAT, which is the basic attention token. So this is a ERC20 token. We did an ICO in 2017. And the way this is supposed to work is that advertisers buy ads with Brave. And then a part of these this ad revenue is given to users who earn the basic attention token. And then when the users earn the token, they can use it to reward creators, and then the creators earn the token. So we call this Brave Rewards. In other words, Brave users get the tokens from looking at ads. And to be clear, the ads are completely optional. So if you don't want to see ads, that's up to you. There will be no ads. But if you do see ads, our reasoning is that you should get part of the money that the advertiser is paying Brave. So you actually earn these tokens, and then you can use them to pay creators to make up for the revenue that they're losing by us blocking ads by default. So the BAT is actually kept in a one-way wallet, which means that once it's in Brave, it can't just be cashed out. In fact, the only way that users can use the token is to pay creators. And this is to reduce the risk of fraud by making it a little bit less fungible. So users can spend BAT essentially by tipping creators or by auto-contribute. And creators can sign up at creators.brave.com to verify they own a website or a YouTube channel, and then they can earn the token. And then the ads appear as a system notification. And what's innovative about this is that the matching happens client-side. So there's no data that's leaked to advertiser. All the inference happens using local machine learning. So if you are interested in hotels in Korea, the browser knows that, but there's no reason the advertiser has to know it. So that's inferred locally. You see the ad locally, and then no data is sent to the advertiser until you click the ad. So this is actually all guaranteed using a zero-knowledge proof protocol on top of the attention token. So these are actually like a form of virtual token that has better privacy than like on-chain ERC20 tokens. So essentially, we can prove to Brave that the user has seen an advertisement without revealing what advertisements the user has seen. So this is very cool because we can prove that the user should be earning money for the ads without getting any more information about what kinds of hotels or cars or anything that they're interested in. But the focus of my talk today is actually Brave Wallet, which is a completely separate product. And this was started in 2018 when I attended ETH Denver. And we decided to build a wallet inside Brave, built-in And many people asked us, why did you build another Ethereum wallet? There were many Ethereum wallets in 2018. But actually, if you think back to then, there weren't that many that were integrated into the browser because like dApps weren't as big of a thing. And the wallet that I think was most used at the time was Mist, which was created by the Ethereum Foundation. And we actually identified some like pretty big security issues with the design of Mist. So to explain what the security problems were, I have to talk about the security architecture of Chrome. So Mist was based on a platform called Electron, which was based on Chrome. And Chrome has a principle of security sandboxing. So essentially what this means is that there are processes that run at a high privilege level, sandboxed from processes that run at a low privilege level. And these processes have separate memory spaces, but they can talk to each other through inter-process communication channels. The things that run at the browser process level or the browser kernel are the most security important parts of the browser. If you think about, if someone hacks your browser, what is the worst thing they can get? The worst would be cookies, right? Like imagine if they got your cookies to Coinbase, they could log into your Coinbase account immediately. If they got your passwords, they could also do that. Things that deal with data stored on disk, that's all in the high privilege sandbox process. On the other hand, the low privilege process, that's called the renderer process, that deals with untrusted data, such as parsing HTML, decoding images, interpreting JavaScript. Because when you go to a web page, and users visit all kinds of untrusted web page, the browser has to parse the HTML. It has to, have entire PNG, SVG, JPEG decoders. All of those are very complex grammars, and it's relatively easy to find vulnerabilities in those because they're so complicated. And the idea is that if I have a vulnerability in the PNG decoder that leads to a buffer overflow in the browser, I should not be able to get your passwords. In fact, I should only be able to compromise the single tab that you're visiting. So that's the idea of sandboxing. However, the problem with Electron, which is what Mist was based on, was that everything ran at the same privilege level. There was no sandboxing. So if you got an exploit in the PNG decoder, you automatically could just get access to the browser passwords or the wallet private keys or anything at high privilege. So so of course Mist, which was based on Electron, had to have access to the private keys, right? Because it was an Ethereum wallet. Furthermore, it was based on a version of Chrome that was over a year out of date. And Chrome, they publish known exploits after about 12 weeks, right? So at a year, there's definitely known memory corruption vulnerabilities you could use. And without sandboxing, it's very easy to go from just an exploit in HTML or an image decoder to just full compromise of the wallet with private keys. And they, I think, around 2018, they actually issued a security advisory about this exact thing that I'm talking about. So, but the point is, we did not win the hackathon. So we didn't get any prizes, and so people forgot about our project until in 2021, we actually decided to just build it in a Brave and launch it officially as a Brave wallet. So right now, we have about 250,000 monthly actives and over 2 million wallets created. So the design is pretty simple. It's built into Brave. It's running at Brave Wallet. And what's important to note here is that we have this implementation of window.ethereum, which is injected into web pages. So what is window.ethereum? It's a very interesting topic because this is one of the only bridges between websites and Ethereum. So this came about because of MetaMask, because they started injecting a global JavaScript API into websites, which allows websites to read Ethereum accounts, read data from blockchains, and suggest the user sign messages and transactions. If you've ever used CryptoKitties, you will know that window.ethereum is how CryptoKitties is able to access your MetaMask account and request you, transfer funds, buy kitties, sell kitties, etc. So that's all done through this bridge. So previously, I worked on the W3C, which was an organization that dealt with like JavaScript APIs, web APIs. So when I started looking at Window.Ethereum and Brave, and when we were implementing it, I realized like there were a lot of ways we could make this more secure. So myself and my coworker Kyle, who is here, and a few of our other coworkers wrote a new EIP called Restrict Ethereum Provider API Injection. The idea behind this is that so the web has a concept of powerful APIs. So these are things like geolocation, camera, microphone. So APIs that are so powerful that they should only be accessible in secure contexts. So what is a secure context? A context you can think of as an HTML environment, or so that could be a top-level page or an iframe. So in this example, we have a top-level page of localhost, and then we have 2 iframes inside that, and then another iframe inside one of those. So that is 4 total contexts, because you count the top and then you count all of the iframes. Each of those is its own HTML document. So what's a secure context? Well, that's very simple. So a secure context is just a context that is HTTPS or localhost, pretty much. You can check if you're in a secure context in JavaScript using window is secure context, which will return true. And so our contribution here is we specified in the standard that window.ethereum is a powerful API because it allows access to wallet private keys. And so therefore, it has to be undefined unless you are in a secure context. So I'm just going to skip this example. So you might ask, what's the point of iframes? Why are they so useful? So let's imagine we're building a website that is a cryptocurrency exchange. We'll call it Binance. And you want to embed a video about how to use cryptocurrency, right? So one way you could do this is you could just embed a script directly saying script source equals example.com video.javascript. And the problem with that is that if there's any vulnerability in this third-party video player, suddenly your entire cryptocurrency exchange is compromised because that JavaScript executes in the same context as the top-level page. But instead, what you could do is you could put an iframe from example.com on your web page instead, and now you have this nice browser-provided security separation because iframe runs in a separate JavaScript context that has no access to the parent page. And also, it actually runs in a completely separate process. So security vulnerability in the iframe will not compromise the parent. And actually, to be specific, we added some more restrictions on the iframe. So we also said window.ethereum cannot be, by default, injected into third-party iframes. These are iframes from different origin than your parent. And also, if the iframe is first-party and it contains the sandbox attribute, then don't inject window.ethereum unless the sandbox says also allow same origin. So I won't explain the full details of this. I'm just mentioning it because the reason why we had to add these restrictions, these additional restrictions, was because of a website called OpenSea that you might have heard of. So OpenSea, if you've used it, it's for buying NFTs, right? NFTs can actually come in a lot of formats. They can include SVG. So SVG is a very interesting format because it runs JavaScript and it runs HTML. NFTs can be entire web apps so that they can handle clicks, they can use any JavaScript API. So, well, that's a problem, right? Because if this arbitrary web app called an NFT is running inside OpenSea, then if anyone makes a malicious NFT, can it just compromise the entire OpenSea website? Well, the answer is no, and the reason why is because OpenSea uses iframes for sandboxing. So this was just a page on OpenSea that I looked at while I was on the flight here. And this NFT, which wouldn't load because I was on a plane and I had very bad Wi-Fi, is an SVG. And you can see they're using an iframe to sandbox it, right? So that the SVG can load, but it doesn't have access to all of the security context on OpenSea.com. So yeah, this is... they're sandboxing this using iframes, and they're usually using third-party iframes in all of the examples that I could find. But someone told us that there's actually cases where they're using first-party iframes, which is very strange. But anyway, because they might use first-party iframes, we had to say like, oh, if it's first-party but it's also sandbox, then we assume it's like a different security context, so we shouldn't put the window.ethereum object in it. So what is the attack scenario, right? Like let me just bring it back to like why we even care about this. Let's say I'm a evil person and I create a malicious NFT, which is an SVG file, which means it can include JavaScript, and I can say ethereum.request, and then I can request a transaction. And then I upload the NFT to the OpenSea marketplace, which anyone can do because it's an open marketplace. And then when you look at my NFT and you have, MetaMask or Brave Wallet installed, it will show you a prompt asking you to sign a transaction. Now, you will think probably that transaction is coming from OpenSea, which is a very trustworthy website. But it's actually from my completely random, third-party NFT, which you don't trust. So yeah, so basically if we look at iframes that are sandbox, we just assume they're not trustworthy. So another very interesting thing is this exact exploit actually happened on Etherscan and on a few other high-profile Ethereum websites, but not because of NFTs, because of advertisements. So the way that websites ensure that advertisements don't compromise the entire website is using iframes as well. So in this example, you go to Etherscan, and there's an iframe at the bottom from bc.game. It's just some random advertisement. And that advertisement calls window.ethereum.request. And that opens MetaMask. And if you're not very careful, you will think, that request is coming from Etherscan, but it's actually coming from this ad. So that's very tricky, and that opens the wallet up to like all kinds of phishing attacks. So the last problem I want to talk about is that the fact that definitions of window.ethereum can be overwritten currently. To explain this problem, I have to explain the security architecture of browser extensions. So this works the same in almost every browser these days. Essentially, there are 3 levels of script permission. There is the background script, which is high privilege, the content script, which runs in the browser tab, which is medium, and then there's injected scripts, which run in the page, which are lowest privilege. So just keep in mind there's 3 contexts. The ones we'll focus on are content script and injected script. So content scripts run in this interesting thing called an isolated JavaScript world, which means that even though they are injected into a page's tab, they don't have access to, actually the page doesn't have access to variables defined in the content script by default. So you can overwrite this by either directly putting a script tag in the web page, or you can just use this like main world parameter to execute things in the page. So to illustrate what this means, let's make a very simple HTML web page. So this is just a page with a single div that says hello. And then let's also build a browser extension. And so this is an extension content script, which is going to run in an isolated world. So in the content script, we're just going to define a bunch of variables. We're going to define a variable called password. We're going to define window.ethereum. And then we're going to actually go look at the div of the website and then change the value inside the div. And then we're going to change some attributes on that HTML. So what is visible to the page? Okay, so if we actually just load the page and then we go into the console, we can look at what is injected by the extension and what actually is visible to the JavaScript in the main world. So first you can see is that window.ethereum is not defined. Remember, we defined it in the second line here. So that's not visible to the page. And then password is also undefined, right? So that variable is not visible. However, you can see that the text was changed to goodbye, and that's visible to the page. So essentially what I'm saying is that if you inject an extension content script, it can change things on the page, and the page will see that, but any other variables pretty much are just undefined. So the lesson here is that window.ethereum can only be called by websites if it's injected into the main world, which is not the default for extensions. The problem is now, JavaScript on any web page can redefine window.ethereum to be anything it wants. And this creates an interesting type of attack called prototype pollution. It's the vulnerability where an attacker can inject their own property definitions into trusted objects where they're not supposed to be able to do that. To illustrate prototype pollution, let's say that we have a website and we define a user object with two properties. We have name and we have is admin. So we expose an API that allows users to update their name, but we don't want them to update is admin, because if they can do that, then they can change other things that we don't want them to have permission to do. So this code looks pretty reasonable on the back end. So it basically checks if object.keys includes is admin, and if so, it just returns early. And if not, it merges the user update with the original object, right? So does this look like it has a security issue? Probably not, because we're filtering the is admin key. So there's a way to get around this using prototype pollution. Let's say that my user name is Alice and is admin is false. So I call update with my name Bob, right? And then Bob, it works because Bob is a normal key and is admin is still false. Okay, now I try to update is admin. So let's try to elevate my permission to admin. That doesn't work because remember in the original code, we're checking if the key includes is admin, and if so, we just return early. But what about this? What if I say update and then I use the object __ proto __ is admin true? That's very interesting because that works. And now I've elevated myself to admin privileges just using a special object that looks very magical and strange. Well, why does this work? This works because JavaScript is a prototype-based language. So when you create an object in JavaScript, there's a hidden prototype linked to the object. And if an attribute doesn't explicitly exist on the object, JavaScript will look at the prototype, right? So even if you can't directly update an object, if you can update the prototype, then all objects that descend from that prototype will be polluted, and they will have a bad property that the attacker has defined. So let's check. Okay, is MetaMask prototype pollutable? So the way I test this is I redefine array.push. So in JavaScript, array.push just adds an element to an array. But I can define that to be something else. So instead, I say, array.push, instead we're just going to log polluted, and then we're going to increment a variable. And so what happens when I load this in my browser? Well, if I load it without MetaMask, nothing happens, because nothing is calling array.prototype.push by default. If I load it with MetaMask installed, I see all kinds of prototype pollution, right? Like it's all being logged into console, because MetaMask is calling, its internal code is calling array.push, but that array.push has been redefined by my web page to be anything I want. So where is it defined in MetaMask? It's defined in this code. So it's registering a JS script called inpage.js, and that runs in the main world, which means anything can overwrite it. So how do we fix this? Well, the good solution would be being able to freeze window.ethereum. So in JavaScript, we have these ways of freezing objects so that future callers cannot update them. We can do a window.freeze, we can set writable false, configurable false. But this is a problem because in Brave, we learned that many users want to use both Brave Wallet and another wallet. So they would use Brave, and then we would call, window object.freeze window.ethereum, and then they would install MetaMask, and MetaMask wouldn't work because their MetaMask is also trying to define window.ethereum. So there needs to be like cooperation between wallets, for us to build wallets that do not have prototype pollution on window.ethereum. So, also it's interesting, if multiple extensions are installed and they're all trying to define window.ethereum, the last one wins, right? So if you install Brave, you install, and then you install MetaMask, and then you install Phantom, because you installed Phantom last, Phantom's definition of window.ethereum is the one that the page will get. So the solution to this is another EIP, which again, Kyle is as an author on, so much credit to my coworker Kyle who is here. And the solution is very easy, right? It's just these providers should have to announce themselves, right? We should define these APIs that allow them to say, hey, this is Phantom, this is MetaMask, or this is Brave, and this is my implementation of Window.Ethereum. And then on the page should be able to tell the user, like, which one would you like to use? Would you like to use Brave, Phantom, or or MetaMask? And then the user should pick, and that should be the winning solution. So that's how we should resolve that conflict. Anyway, that's my entire talk. So thank you for your time, and if you want to contact me, you can use any of these channels. So, thanks.